maybe you can tell us a bit about your background, because we spoke recently a while ago, and it wasn't until then that I realized that you had made the Oklahoma State 350 standard cell library, which was the first standard cell library that I used. And I think probably a lot of people involved will have heard or used it, but not know that you're the person behind it. So maybe you can tell us a little bit about how long you've been involved for, what kinds of stuff you're interested in, and what you're doing at the moment.
Well, my area of research is in computer arithmetic, and I love algorithms and implementations of digital logic, specifically for computation arithmetic. And I did a lot of that work in grad school thanks to my fantastic PhD advisor, Mike Schulte, and who now works at AMD. But it was really great. I wanted to go in. I wanted to try to see how academics was, and so I started working in academics, and I quickly got acclimated to people not really having tools or cell libraries to help me. They could give me cell libraries, but they wouldn't really provide them that I could use them in my class or I could use them in research, and they made it kind of restrictive. Not, I definitely understand their thinking on that. So I really was kind of really against the wall, and I didn't know what to do. So I was talking to a friend of mine at University of Utah, and I was telling her I felt like a pirate. I felt like I could either go down with the ship or try to sail forward. So I tried to learn as much as I possibly could, and I was really fortunate that there was a really fantastic faculty at Stanford, Mark Horowitz, who really hooked me up with other people to learn this standard cells more, how it's done and how it's done effectively. And so even though I'm still doing computer arithmetic, I really wanted standard cells and SOC to kind of do that. And so I try to give back to what Mark did to me by just anything that I do for standard cells or anything I try to release to help others. And so I've been doing that I did that one. And then I did, there's one called the free PDK. I did a standard cell library for that one. And then I did a couple others for some of the EDA manufacturers. And then now I'm doing the stuff for Skywater and Global Foundries.
Yeah, we'll get onto the Global Foundries one in a minute. So another thing that also my viewers might have seen go by is the work that I did with Teo on is adder optimization. And he's one of your students, right?
Yes, he is. He's one of my fantastic PhD students who, it's always a great thing when I have students who come in and they don't think I'm crazy. And, he was very helpful in trying to do stuff. And I always tell them about open source and how important I believe it is to the society and like what I do and what you do. I think that's, it's underestimated on how impact it has on so many people. And Teo took that, that cause to heart. And, I was doing some work with him on adders, and he said, well, I'm going to make a tool that I can give out to other people to make adders better. And that's how that kind of came into reality, which is really fantastic.
Yeah, it was really great to collaborate with him on that project because then I did a bit of work on, we taped out the 4 different topologies on MPW6, I believe.
Okay.
And I built a bit of infrastructure along with some help from people on the course to try to measure how fast they are so we can make a comparison on Sky 130.
That's great.
So it was a really great project. And his work was based off of Proppy's work.
Yes.
So that he could do all of his work in a Jupyter notebook on the cloud. Yeah. And to me, that seems like, when people ask me, like, what is the point of like open source EDA tools, and aren't they like so kind of poor and slow in comparison to the proprietary ones? And I always say, well, I think that there's a couple of accelerants And one of them is that if academics can share their work by like giving a single link to a web page that lets other people reproduce it and then make a pull request and validate the
Yeah,
results and make improvements, and that is actually we can, and that can be done on a PDK that we can actually manufacture,
right.
then to me that seems like it's going to really accelerate the progress of the open source tools, and um, gives like an amazing ability to innovate and do research. And I was just wondering, like from your side, as like in the fully academic world, what's your take on that? Does that sound like a reasonable thing to say?
Very much so. I've always been a huge proponent that open source is the key to innovation, especially for EDA tools or electronic design automation tools. Um, I Some people in the commercial world that I've talked to, I don't think they believe, they don't, they don't, I think agree with what I'm saying, but I do think they help each other. And it's the same way with what you just said is when you can take something and produce it and fabricate it and say, hey, look how great it is. Um, you can help those commercial tools actually get better too, as well. And you can push the envelope. Otherwise, you're relying on what they produce, which is could be biased. It could be not considering other things that other people. I think people are wonderful. They come up with great ideas. Teo's Adder's work. He was able to outperform some of the commercial tools in some of the synthesis results that we did some analysis on. So it's obvious that they can help each other.
Yeah.
And I, yeah,
And now that work can be like used by everyone doing open source, not just chip design, but with FPGAs as well. So
yes, very much so.
really very great and useful work. Yeah, so I'm very excited to see how that progresses, and
Yeah.
like building on the work that Proppy's done with the kind of developer experience side of things, making
Yeah,
it really easy to experiment without needing to install loads of stuff on your computer.
he is another one that's like also very helpful, and he's so nice too, and
Yeah,
just extremely, I can help you, and I think what he's done too is also very innovative.
yeah. So we were having a call for my course. We have a weekly call and chat about stuff that's going on. And we were talking about the new open source PDK from Global Foundries, GF 180 or Glofo 180. I quite like Glofo. Um, and a bunch of questions came up in the call, and then I just reached out to you and said, "Could we like do an interview?" And you like immediately responded yes. So thanks very
No
much for
worries,
that.
no problem.
And
Thank
so
you.
let's get started on some of the questions from the people on my course. So um, the first one was, when you're teaching the design of standard cell libraries, what do students struggle most with?
That's a great question. I think one of the more difficult things to understand about standard cells is that they're not like traditional layout. They're meant to really work with the EDA tools. So they're planned layout um, where they're designed so that all the pins can actually connect together, and all the tools can interface to them. So they can be slightly larger than a optimized custom layout, and so you have to really craft them so that they always adhere to these options. And so I think having that difference is sometimes students don't really understand that process. And then once I explain them how that's working, they kind of get it then that, oh, these are like, it's kind of like saying I'm providing a generic map of the city, and it may not be accurate, but it helps everyone get to the right destination. And I think
Mm,
another challenge too is just understanding how standard cell libraries typically you characterize them, which means you run SPICE thousands and thousands of times to get information that the system and chip tools can use. So understanding how to get that information into the characterization tool, and then is it the right information? Is it the wrong information? So, for example, you can forget parasitics, capacitance, resistances. If you don't incorporate those can really cause your characterization not to work really well. And so once students understand that all these things help get that right information, then it helps them go forward a little bit better.
Great answer. Okay, next question is, what do you think engineers least understand, but should know about standard cells?
Your questions are fantastic, so it's great. I think one of the things that most people think of is that there's a standard cell library out there. It's always correct, and it's not always correct. Typically, good standard cell libraries have good characterization, but they also have multiple corners. And if you don't have the right information in those standard cell libraries, they can actually be mistaken, and you can get really bad information on it. So I think good standard cell libraries involve good design and good testing to make sure that they're actually created well as everybody can use them. I make mistakes, and everybody make mistakes. You can forget to include parasitic effect, and if you don't give it out to the public, nobody will see that. And so I think that's something engineers kind of, at least they don't really understand, is that they think, oh, I got a standard cell library, this should work every time. It doesn't always work all the time. It could have some issues.
Yeah. And just for people watching this, if terminology is mentioned, like I was just thinking when you mentioned corners, I remember
Yes.
when I was getting started, that was like I don't know what that is. I have a terminology section on my zero-to-asiccourse.com website. So if you just go there and search for any terminology we're using, and that will hopefully uncloud any issues.
Yeah. I
Yeah,
apologize
so
for giving
no,
that
it's fine. I just got to keep an eye on what, like, even though I'm only kind of 2 years into this, so I'm not exactly a beginner anymore. That I remember when I first got started, there was so much terminology, and I was like, "What is a corner? The corner of a wafer, but wafers around. What does it mean?"
Yeah,
So yeah. So next question was, what is your tool flow when you're building and characterizing a standard cell library?
that's a great question too. So I love open source tools. That's what I think that is what is the bread and butter of everything that we do. So I try to create layouts that I in Magic, which is an open source tool developed by Tim Edwards, or it was originally devised by John Ousterhout, who was at Berkeley, and now Tim Edwards, who's done a tremendous tool um, for layout editing. And so I use that tool to create all the layouts from the PDK from a given schematic. And so I'll take the schematics, I'll put them into a tool called Xscheme, which is an open source tool. And then I'll use the Magic layout to go back and forth to try to figure out how to best to make the layout. And what we typically do is we try to make the cells a set height, and not all standard cells are the same height. Like there are some standard cells commercially that have different heights inside, but traditionally, like open source standard cells, they typically have the same height. And so we measure the height in this term called tracks, and tracks are defined by how high they are. They're usually like 7 track, 8 track, 9 track, 12 track, and they're usually based on the pitch, which is the distance between pins or metal layers. And so we try to create that track height to fit everything, all the cells in the same height. Now you can imagine like something like an inverter, which is a really great gate, but it's very small. And then if you make the track too small, it makes it difficult to make the more complicated ones like D flip flops. And so once we create the layouts, and we'll typically do like maybe 5 to 8 layouts of gates, and then we run it through a characterization tool to kind of figure out the performance, and it runs SPICE multiple times. Uh, we are working on an open source version of a characterization tool, but right now we use a commercial tool for characterization until we get that open source tool. We'll continue to do that until that. But we try to create the libraries or the information, which is usually in something called a Liberty file, and then that's used in the place and route tool. So we'll test it, see if it works, and there's always it doesn't work. There's always you put two cells together and there's some DRCs, or you didn't count for something. And so you have to go back to the drawing board, and then you'll keep on going back and forth. And then we'll add more cells. And I've been doing it for a while, so it's a little easier for me. The 180 cell library we just did took us about 2 months to do, to create all the different tracks. And we created ones for 9-track and 12-track.
Cool. Great answer. So I'm going to just jump to another person's question because it fits quite nicely in here.
Sure.
How many cells are enough cells? Because I think most people who've done a bit of digital design know that you can basically make all digital logic out of a NAND gate.
Yes.
And then if you have a flip-flop, then you can build everything. So flip-flop and a NAND. So
Yeah.
how much is enough?
Yeah.
The question is, how many cells are enough cells? You can cover all the functions with flip-flop and NAND, but things improve adding more logic functions, often increasing in complexity and drive strengths. But what's the marginal improvement of adding the 10th versus the 100th cell?
Right.
And how do you decide the optimum number of cells to design?
Yeah, it's a great question too.
That's from Thomas Parry, by the way, and the previous questions are from Eric.
Thank you, both of you. That's really great. Fantastic question, because I don't think it's answered anywhere as of yet. I do feel that commercial tools know the answers to many of these questions, but they're less likely to give that information out. But typically, the answer is that it really doesn't matter. What we traditionally do is we try to make the correct number of cells that support open source and commercial tools for high level synthesis. And each high level synthesis tool, sometimes called HLS, will have a minimum number of cells that they want in a library. And there's lots of reasons for that. They're really more theoretical in nature. But I think some tool manufacturers have like 5 cells that they want, which I think they're like NAND, NOR, D flip flop, inverter, and one that I didn't realize, XNOR, which seems kind of non-intuitive. And then beyond that, it really is just, I think it needs a lot of study to be done on how that's being done. So I think who knows what the right answer is. Commercial tools or commercial libraries will have thousands of cells. Is that necessary? I don't know.
Yeah, because I only have experience with open source tools and the open source PDK, which is sometimes a limitation because people ask me like, what's the difference between proprietary tools or whatever.
Yeah.
So I don't have many data points to go on, but I was interested. Sky 130, the high density cells that are the default ones. I think we've got about 150 cells in that library, and it looked to me like when I did a very quick check of the Glowfo 180 that it's less than that. It's more like 70 or 80.
Yeah, it's a lot less. And I think this is one of the other reasons why open source tools are extremely important, is that, I think the more that you can put out there needs to be studies on what's the right number of cells. What if you vary the number of cells? Will it be better for your design or less? Will it cause more errors later when it's fabricated? These are great questions that I think is a real reason why open source is so important. And that's why I try to put everything out there so that other people can use it and then see how it works.
Yeah, it would be cool to be using a standard cell library that you've designed on real silicon. So maybe we can jump to that quickly.
Sure.
So you're working on a standard cell library for the GF180 process at the moment, right? And there's already a set of standard cell libraries. So why do we need another one?
So it's a great question too. Google contacted me about, hey, can you create an open source version for GF? And I was like, yeah, sure, no problem. And I think one of the reasons why they want that is it'll be completely open source. I'm not sure who created the other one from GF, and there may be some NDA requirements for that. And then I also think that the GF library doesn't have the right voltage. I think it was 5 volt. and they wanted one for 3.3 volt. And so we wanted to create for GF, and there's three sets of GF cells. I think there are PDK. There's a GF180 MCU, GF180 IC, and GF180, I think, light or something like that. And so we wanted to create libraries for all three of those technologies that are not currently available, and then also make them public source, open source.
Great. Maybe, yeah, it'd be interesting to characterize them when they're ready.
Yeah.
Yeah. Okay. So maybe we can talk a bit. A question from Farhad was, how far are we in terms of open source tools from the commercial tools, and how far away from now do you think that open source tooling will be competitive? And I guess maybe that also ties into another question from Eric, which is, can you share any details on the open source tool called Liberate, which I think is
Yes.
the alternative to the proprietary one you're using?
Yeah, definitely. So um, I think with a lot of the work that Google has done, as well as Skywater, that really helped spur the whole industry to try to, or not the industry, but a lot of people like what you've done, which has just been amazing, to create this open source initiative for a lot of people. So I think the more that gets out there, the more that it will be more closely tied to what commercial tools can do. I still think there's a ways off, and I'm thinking maybe 5 to 10 years, that we'll see more of the open source tools might even outperform more of the commercial tools. However, I don't think they'll ever totally surpass them. And as I said before, I think that they should sit in the same ecosystem. Um, and that if a commercial tool sees an open source tool, it's a really great tool. Hey, maybe we can do the same in our commercial tool, and they should help each other. And I think you'll see more of that as we go forward, in the future. And then I think the other question was related to, what was the other question? It was
About
the
Liberate?
open source. Yeah, so we're working on an open source version of Liberate. Liberate is the tool from Cadence Design Systems that we use for characterization, which has actually gone through, I think, 3 or 4 different naming structures, which is typically for commercial EDAs, and they've settled on the name Liberate. And so I think we're about 2 to 3 months away. We have a version that is working kind of now, but it's not very. There's a lot of bugs in it, so we're still trying to figure out those bugs. But we hope to have this open source version that we run in Python, available, that people can use it for all the libraries that we create, and it'll. I'm also trying to do it for the previous libraries that I've done too, so that you can see that it's competitive with what Liberate can actually do. And I'm always inspired by people like yourself and Tim Edwards, whose contributions are just tremendous. What we can do as long as we work together. I think that's really great. And so my goal is to do something like what Tim did with Magic, is try to create something that anybody could use or benefit from, but also improve and create a completely open source. And so I think next 2 to 3 months, I'll have something that'll be publicly released, on the GitHub site.
Great. It's actually a question I've had quite a few times, is people saying, I want to design my own standard cell and then use it
Yeah,
in the flow. And it's actually quite a complicated thing, because you've got to draw the standard cell and then characterize it. And then somehow you've also got to get the tools to pick that up and understand that it's an option.
yeah. It's like I said, like your great question in the beginning was like, what do students don't quite understand? They kind of think standard cell libraries are the same as normal layouts. They're a little bit bigger, and they are designed to fit into the same structure that the tools can use. And so they're once they understand that, and I think that's why I try to always put all the scripts that I do, all the layouts, all the schematics into my repository, so people can download them and then recreate them. So yeah, there's the opportunity that is there for anyone who wants to do that. And I try to do the same for what Tim Edwards does to the public, and as well as yourself, and anybody who's interested. They're more than willing to contact me, and I can help them create their own standard cell library too as well.
Excellent. Well, let us know in the comments if that's something that you're interested in, and leave a comment down below. And in the description, I'll leave a way to get in contact with James. So thanks very much for that, James.
Sure.
Okay, so moving on then. Here's another question from Eric. Do you think that the automated layout of standard cells will be competitive with hand layout in the nanometer processes?
Um, I don't think so. I mean, there was a lot of, I mean, when you mean automate, you mean like the automatic standard cell creation or?
Yeah, I think because I work with Staff a bit in Chipflow, and he has a library, a system called PDK Master, I think, or I
Okay.
might have got the name confused, but it's meant to generate a standard cell library.
Yeah. So I did some work with a fabulous researcher at NC State called Rhett Davis, and we wanted to create something called a free PDK, which is a non-fabricable technology. We did this about 20 years ago or so, and I used some automatic generation tools to create standard cell libraries for that library called the free PDK. And I think they're really great for the larger technologies, but I think for the as the technologies, the feature sizes are getting smaller, it becomes less likely that they'll be used because there's so many little challenges that happen. Some of the smaller feature sizes use different rules for different because they're 3 dimensions instead of two, and so they have a dual pattern technology where they're looking at different layers in different dimensions. And so some of those automatic systems may not work as well, but I think that they're still useful and they're still important to the society. And so I think they may actually be really great for the future. I know a lot of researchers
Yeah,
are working right now on incorporate machining learning into these EDA tools. And I know the fabulous work with Andrew Kahn out at UC, University of California, San Diego, incorporating that into the Open Road tool. I think that will be, you'll see more of that. And I think that those machine learning things could be translated into automatic generation of standard cells. But I
yeah,
do think they're a little bit off. I think that might take a little bit longer than,
yeah.
um, in my opinion.
Yeah, so I got the name of Staff's library wrong. It's called FlexCell. And if
Okay,
anyone's watching and is interested to know more about that, I interviewed Staff a while ago on this channel, so you can check that interview to find out more.
cool.
And also, let's give a shout out to Open Road, who you mentioned, and it's been good to see them kind of getting a little more active in kind of putting themselves out there. I think there's a bit like you in a way. You're like it's there's a lot of people doing very important work in the background, and often people from the academic side they don't really put themselves out there. So like Open Road only just got a LinkedIn profile set up recently. So
Yeah.
it's good to see people a bit more findable and like taking pride in their achievements. So that's good to see that.
Yeah, they are also committed to helping the whole community. I know Andrew Kahn and then Tom Spyru
Yeah,
are really great at trying to help push this whole open road thing, which I think is
yeah.
much needed.
And their tools are absolutely central to the open lane ASIC flow. Wouldn't exist
Yes,
without them. So it's important to
yes,
acknowledge that. Yeah, we're all building on the shoulders of other giants.
yes. But I
Okay.
think what's great about us is we're, it's a family. We're all working together to help each other, and I think that's important. I don't think commercial tools have done that, before this. And I think they're starting to realize that they can gain a lot from open source.
Yeah. Yeah, and there's loads of opportunities to get involved as well. So,
Yes, yes,
yep. All right. So here's another question: are there any circuit families from the past, like dynamic logic, pass transistor logic, domino, multi-output, etc., that deserve new attention now that Moore's law is slowing down?
yeah. That's another fantastic tool question. I personally think that this is a really great question because I tell my students all the time that the best innovations were innovations that came earlier, and that maybe people forgot about them, and
Yeah,
that
like
they kind of
asynchronous logic.
yes,
Someone was talking about that on Twitter the other day and posted a video which I watched. I think, and it was in Matt Guthaus was the person that facilitated the interview. I'll post a link to it in the description. But it was like people kind of it was like a big useful thing, and then it got completely forgotten because of needing to reduce noise and using a clock.
Yeah.
But when people were hand wiring backplanes, and then that just became the status quo. And even though now we can do like very low noise and everything is like incredibly small and predictable, and so probably noise wouldn't be a problem like it used to be. But everyone is now like on the clock all the time, and so you lose like these potential benefits that have been created once and then forgotten. So yeah, I think it's a great question as well. Sorry to interrupt you.
Oh no, it's good. I think those families are very, very important for future standard cell libraries. For example, certain libraries have things like gated clock cells, and those are extremely important for low power domains, so that they turn off certain sections of the chip that are not used, and then that way they can conserve power for the whole chip as it works. And so, getting those technologies to work really needs using some of those circuit families to really rely on how to do that. And then that gives a subsequent question is, how do you get the characterization tool to see those correctly? And I think that's still a challenge. We did a gated clock cell for the standard cell library for Skywater, and it wasn't necessarily straightforward, just because the characterization tool didn't know what it was looking at. And so I think those logic families are extremely important, and I think that they'll come back. And so I always tell students, you need to know about history and how to innovate the next generation. So always remember those things, because they will come back at you and they could help you tremendously.
Yeah. So that video was with Rajit Manohar from
Yes.
Yale, and it was Tommy Thorne posting that on Twitter. So I'll link that up in the description.
Yeah, Rajit's another great person who's done some fantastic stuff at Yale, who I believe was originally part of the original Magic foundry when he was at Cornell, and then Tim Edwards took that over. But he's tremendously contributed to the asynchronous world, and I think his stuff is really fantastic as well.
Yeah, and his work is open source, and it looks like it's something that people can start experimenting with. So that would be excellent. And yeah, another thing that comes up often, but I so far haven't seen anything taped out on the Google shuttle. So if anyone's out there watching and wants to do that or has done it, then please get in touch and we can have a chat about it. Maybe get you on the air and interview you for the channel. All right, cool. So I think we're down to the last question now, which is a surprise question. Do you have any theories on why NVIDIA would make a 7.5 track standard cell library?
So that's a great question. I did, like I said, the 12T and 9T track libraries for Global Foundries for the 3.3 volt MCU. And one of the things that you see as you go from 12 to 9 is that it compresses it pretty nice, compactly. And so you really have no room because you're making it smaller. So you have to go horizontally and to really compensate for the fact that you're getting smaller. So the 0.5 kind of is indicative for me that they couldn't make it work at 7. So they had to go to 7.5. And so the smaller that you get, the more density you get for the standard cells. And so my guess is that's why they went to 7.5 track, because they couldn't make it 7. And we actually tried to make a 7 track in the GF cells, and we couldn't do it. So we had to go to 9, or we couldn't do it easily. So maybe we'll get to it later, but you see this like where, again, they're all the same height, and so they have to really cram everything in there. And that's probably what happened when they made this standard cell library. It's a great question.
Yeah. Great. Well, we've got to the end of all the questions. So I just want to say thanks again for your time and for answering everything. Really good to get you on the channel. And
thank you very much for having me. I really appreciate it. And thanks to you and your your viewers as well. I think we're all important and we all can contribute.
Yeah, and looking forward to some more collaborations in the future, and maybe we can do
Yes.
a how to make your own standard cell library tutorial together
Yeah,
sometime. That would be cool.
that'd be great. I'd love to do that.
Okay. Well, thanks very much again, and
Thanks.
yeah, that's it.
Thank you, everyone.